Hi, good morning, everyone. How are you doing today? Good, thank you. Okay, so we will continue to talk about rotational motion. We have introduced angular acceleration alpha. We have talked about torque, how to calculate torque. We also talked about how to calculate I, the rotational inertia, sometimes it's called the moment of inertia. Now we're ready to put it together to solve some more questions. There are a lot of problems that has a fixed stationary axis, meaning that you're rotating in the same location. But there are also a lot of other problems that not only you are rotating at the same time, you are also moving. So you are rotating and you're also moving. So there's a rotation involved, there's a translation involved as well. Like a yo-yo, like if a marble rolling as it going down a ramp, right? So it's rotating while translating. So this type of problems involves a combination of translational motion and rotational motion. So we're going to see a few of these different questions and see how we can split the motion into two parts. In terms of the center of the mass, of the object rotating, but if you focus only on the center of the mass, or if you view the object as one point, you only see it going down, right? Moving in the translational motion. And around the center of the mass, the object is simply just rotating around its own center. So you can split this complicated motion into two parts. One is translation, one is rotation. So consequently, our energy terms will be split into two parts as well. If you look at the translational part, it's simply the kinetic energy of your center of the mass moving, 1/2 mv squared, right? This is what we are familiar with, the kinetic energy terms. So use the center of the mass for its velocity, the velocity of the center of the mass. The second part is around the center of the mass. The other part is rotating. So you will have kinetic energy for rotation. That's 1/2 I omega squared. Okay, so 1/2 mv squared is for translation, 1/2 IV omega squared is for rotation, and it has both translation and rotation. So total kinetic energy is simply these two added together. So let's start with looking at a question we can answer qualitatively. We have a block and a ball. They have the same mass. You start them from rest and let them go down two identical ramps. The block simply slide down, right? Assume there's no friction, and the ball will have to roll down the ramp, rolling without slipping. Which one will have the most kinetic energy at the bottom of the ramp? Would you think it's the block, or would it be the ball, or maybe both of them have the same one? So you can see that the difference between the block and the ball is the block is simply translational motion, is the only motion it has because it doesn't rotate. The ball will have translational motion as well as rotation. So these are the two different, the difference between them. So which one do they have the most kinetic energy at the bottom? So I'm gonna go ahead and give us a minute to discuss, and then we could come back to vote. Okay, so take a screenshot before you head out to your breakout rooms. I'll see you guys in a minute or two. Hi, everyone. How are you doing today? So any thoughts about this particular question? How will we be able to answer it? Feel free to type in the chat if you could not use your microphone. So I do encourage you that you use your microphone if you can. Okay, thank you for Rosalie for the text. I think they'll have the same because they both have the same potential energy due to gravity. What do the rest of you think about that? They all are released from the same height, right? So they have that much energy to work with. And in the end, the potential energy transformed into kinetic energy. So they'll have the same at the end. What the rest of you think about that? All right, so we have some agreement from Nicholas. What about Mark and Esteban? What do you think about that? So one is translational only, and one has rotation as well as translation. So one might think if the two type of energy, would that be more than just the translational? But also that's a distractor. We have to focus on, okay, yes, they have, one has one type of energy, the other one has two types of kinetic energy, but where does that all come from? They eventually all come from the same potential energy, therefore they end up with the same kinetic energy, no matter it's one type or two different types. So the same is correct. So I'm going to say good job, very good job for Sally. And I will see you shortly after we return to the main session. All right, let's take 10 more seconds if you haven't voted already. Okay, any last minute vote? All right, I'm gonna go ahead and end this. Let's take a look. Looks like our results is exactly tied between choice B and choice C. One of them says the ball has more kinetic energy. Choice C said they have the same. Okay, so anybody would like to share their reasoning for either one of them, or a possible reasoning for supporting either choices?
I thought it was B because at the bottom, so they have the same mass, and they're under the same gravitational field and they start up at the same spot, right? So
Mhm.
they end up having the same translational kinetic energy, the 1/2 mv squared,
Ah,
but
okay.
the block is not rotating, so its rotational kinetic energy is 0, but we're told that the ball is.
Mhm.
So it doesn't matter how fast it's rotating if they have the same translational motion, kinetic energy, sorry, and the same, and even if it's rotating a little bit, that's greater than 0. So that's why I think it's E, because any little bit of rotational plus the same translational is more overall.
Mhm. Very good, very good. Okay, so one of the possible reasoning, let me try to reiterate, summarize everybody's contribution is voting for B, the ball has more kinetic energies because other than translation, the ball is also rotating, whereas the block is only translation. The possible reason to vote for C could be, and also one mentioned about, also you used the conservation of energy argument in your reasoning as well, is what kind of energy they have to begin with. So they have the same potential energy. So very key point to figure out which one is correct is, well, okay, for the ball, conservation of energy transformation is potential energy going to kinetic translational only, right? 1/2 mv squared. For the, I'm sorry, this is for the block. For the ball, it's the same potential energy, we all agree, right? They start from the same height. And with that, well, we used conservation of energy approach before, we only counted 1/2 mv squared because that's the only type of energy we have in terms of kinetic energy, right? So in the ball's case, do you think it will go 100% to just the translational, or would it also at the same time go to the rotational energy? So would these two be combined to come from the potential energy of the ball? If it only goes to the translational motion, then you might wonder, well, where does the kinetic energy for the rotation come from? It has to come from somewhere, right? The only place for the rotational kinetic energy to come from is also coming from potential energy. So yes, so they have, the ball has mv squared as well as 1/2 I omega squared. But the difference is, that's the difference. But 1/2 mv squared for the block is a different value than 1/2 mv squared of the ball. So in fact, because the ball also has to rotate, the kinetic energy for the translation would not be as much as the block. It just has less energy to be to go to the translational motion. I hope that makes sense. So if you have potential energy, let's say 100 joules for the block, all of that goes to translational motion. For the ball, maybe 60 joules goes to translational motion and 40 is used on the rotation of the ball. But if you add up the kinetic energy, they should all have the same amount of kinetic energy. That's also that's all 100 joules, which equal to the potential energy that they started out with. Okay. Okay, so C is actually the correct answer. So we got to be careful what is controlled, what is given as the same. So this is the next one is similar to the previous question. It's about a race using different shapes. You have a hoop. Hoop is like a ring, and a disc, a cylinder. They have the same mass, same radius. They will start rolling down, start from rest. Which one will win the race? Okay. So I know you have probably done this already, but let's just do a really quick vote of your, if you have wanted to change your answer at this point, you can, to have a prediction which one will win the race, meaning that which one reached the bottom first. And then we're gonna take a look at the demo to see if our prediction is correct. All right, 10 more seconds. So if you want to add to your prediction. All right, so I'm gonna go ahead and end this. Let's take a look. Majority, slightly more voted for the disk, and we still have quite a majority voted for A. Or maybe they tie, maybe they reach the same at the same time. So to answer that question, let's take a look at the demo to see which one will win the race.
Why are dental companies
Okay. Let me skip this.
of inertia on a rolling disc? This is a solid disc. It has moment of inertia 1/2 m, the mass, r, the radius, squared. 1/2 mr squared for this solid disc. This is a ring of material. It's hollow in the center. All of its mass is concentrated at the outer radius. The radii of these two are the same, but this one has a moment of inertia of mr squared. So it has a larger moment of inertia, assuming the masses of these two objects are the same. The masses of these two objects
Not know why that all of a sudden froze, but let me try again.
matters is the radius, which is the same, and the distribution of the mass between the center and the outside. So we're going to release both of these from rest at the top of this inclined plane and ask which one of them wins the trip to the bottom. Will it be the one with the larger moment of inertia, mr squared, or the one with the smaller moment of inertia, 1/2 mr squared? So as you can see, the winner is the one.
Okay, so we saw it's the disk that win the race, and the disk has a small moment of inertia or rotational inertia. Would anybody would like to explain why that is? You can also type in the chat if you like. So why is the disk reach the bottom first?
So based on my answer from last time being wrong, since they need to have the same final energy, because they had the same potential energy from having the same mass and same height, they're gonna have since they're gonna have to end up with the same energy, since the mass of the disk is concentrated more towards the center than the mass of the hoop. The disk is going to have less of rotational kinetic energy. So in order to balance out the ratio, like the proportion, to have the same final kinetic, the same final energy, it's going to have more translational kinetic energy, whereas the other one has more rotational kinetic energy from having a higher moment of inertia. So it's got to have lower translational kinetic energy.
Yes, very good. Thank you, Juan. I'm glad that the previous question helped you to answer this correctly. The ring will have a bigger eye, so the ring will use more of its energy to rotate itself, whereas the disk has a smaller eye, so it doesn't need to spend all that much energy on rotation. So give it more energy to be used on translation, given that the rotation plus the translation going to be a fixed amount to begin with. Very good. Excellent. Now, this is a very similar type of question, but it's reversed. Instead of going from the top, that they start out with the same amount of energy, and it distributes into kinetic, translational kinetic energy, and or the kinetic rotational energy. This is from going from the bottom. Bottom up, they move with the same V. You can see that that's very important. One is a block, one is a ball. Which one will make it furthest up the ramp? So you can see this is the reversed. This one will have only kinetic energy 1/2 mv squared. For the ball is 1/2 mv squared plus the rotational energy. See, this one, you give it the same kinetic energy to begin with. So the ball overall has more energy than the block, which means when all of that is translated to mgh at the top, this one will have a bigger height than the block. Okay, so you can see why they're going from the top to the bottom. The same argument applies. It's conservation of energy, but if you're going from the bottom with the same velocity, meaning that the ball has more energy to begin with. If they're going released from the top with the same height, then the ball will overall have a smaller velocity of the center of the mass, smaller translational velocity. Okay, so that's it's a subtle difference between these two types of questions. So we are looking at a lot of these kind of problems. They're called rolling without slipping, and you might be wondering, well, what does that mean? So rolling without slipping is if you imagine that you have a disc that you can roll it on the surface, it doesn't slip. It doesn't slip and set back. So that is an important condition that help us relate V and omega together. So in these calculations, we say, well, the translational velocity is the velocity of the center of the mass of the object, because we are viewing the object as one point, and simply this one point is moving. So that is the center of the mass. And the rotation, we're using omega. So how is the velocity of the center mass related to omega? Oh, so okay, one wants to take a look at the previous slide.
Oh, sorry, it was the one before that. The one, yeah, that one. Thanks. Thank you.
No problem. So we can find a relationship by, let's say you have, think that this is the ball or a disc. You trace this point, and this point is simply going in space, right? Like the pink trajectory that was showing. That if it's rolling without slipping, meaning that if you roll all the way around for another one revolution, the circumference of your disc is exactly how much the center of mass has traveled. Does that make sense? Think of this as your bicycle wheel. Your bicycle wheel roll on the ground for one round. So how much distance it covered is the circumference of your wheel, right? And that is because it's rolling without slipping. If it slips, then the circumference is not going to equal to the distance it traveled. But if it's not slipping, these two must be the same. So to calculate the velocity of the center of the mass is the distance it traveled divided by the time. So the distance traveled is exactly equal to the circumference of the disc or the wheel, because it is rolling without slipping. So that's why these two are equal. And 2 pi over t is simply our angular velocity omega. So V center of the mass is equal to omega times r. That is a equation that we know to be used for rolling without slipping. Now you may think this is so looks so familiar to me, because previously we were saying velocity of any linear point is equal to omega r. Okay, so that's always true. But here we are saying this is the velocity of the center of the mass, okay, not just any one point. is the center of the mass is equal to omega r. And this is true if you're dealing with a rolling without slipping type of problems. Okay, so whenever you see rolling without slipping, you can replace this V with omega r. Okay, or you can replace omega with V over r. So having that, given that type of treatment, we are able to use it energy approach to help us solving a variety of different problems. So let's take a look at an example, a conservation of energy example, calculating a yo-yo problem. Okay. So we have a yo-yo with mass m and radius r, starts from rest. When you release it, it's going to unravel the string. It's going to rotate at the same time. It's going to fall. Right. So this is a rolling without slipping situation. It's asking if you release it from a height h off the ground, what is the velocity of the center of the mass of the yo-yo after it falls for a height h? Okay, so we said, okay, it seems to be using a conservation of energy approach. So we have to define our system, right? So we treat our system to be our yo-yo plus the Earth, because we want to be able to talk about potential energy. So I'm going to include Earth in my system. And the initial and the final moment are usually, in this case, pretty obvious. Initially is when the yo-yo is at the top, final moment when it falls for a height of h. So the energy, different type of energy, we can label it and then put it together. So initial energy here, you're at the top, you're not rotating, you're not moving, you only simply have a height above the lowest point. So what type of energy is involved? It's simply potential energy. That is mgh. Well, this capital M because that's what's given. Mass of the yo-yo. Final energy is kinetic energy only. There's no potential because we define the lowest point to be our reference point. So we don't have any potential energy at that point. So for kinetic energy, you have two parts. You have translational part, you have rotational part. So you have to consider both of them. This one is simply 1/2 mv squared. V is the center of the mass squared. The rotational part is 1/2 I omega squared. Okay. Input is 0. There's no external force. It's trying to increase its speed. We consider Earth to be part of the system, so the work done by gravity doesn't do any work. Output is also 0. We are not thinking about air drag or anything here. So really, that's it. It really just have all of its potential as becoming the kinetic energy. So that's it. So to set up our conservation of energy equations, you can plug in these two terms into our conservation of energy equation, and the approach is very much the same as before. Now to solve for the center of the mass, this is what we're trying to solve for. We need to replace omega with v so that everything is represented using one variable. So just to do a little bit more substitution, omega is v over r, right? So this has become v over r squared. The one other thing we need to replace is our rotational inertia for a yo-yo. What is usually the shape of the yo-yo? Is it like a disc?
If we're gonna like assume that it's that like it has the same density throughout, then we could say it's a disk.
Yeah, so we will have to make an approximation to say it's not a ring. Obviously, you have mass all the way throughout the center and assume it's homogeneous to treat it as a disk. Then we can use a 1/2 mr squared to replace our I. Once you do that, you can see everything is a given quantity. M is given, R is given, H is given. The one thing you don't know is V, the center of the mass, and you can solve for that. So the final result is given here, that if you plug in I and omega, you can set the potential energy equal to kinetic from the conservation of energy equation, and you can calculate the center of the mass. Actually, it does not really depend on the mass of the yo-yo. It's square root of 4/3 g times h. So that's one using an energy approach to solve this type of problem. This is a very classic problem, so make sure you know how to do it. I'm going to move on to another problem, but it's essentially the same as this. Okay, so instead of letting it fall, we let it roll down. This is a hook versus disc problem. That's the demo we just saw. We have talked about the reason using a qualitative reasoning, but what if we wanted to calculate it and actually show the center of the mass speed for the two different objects, showing that the disc actually have a bigger V than the hook. We would be able to do that. So we start out with treating this as a generic shape. So right now, this is just an object with a I. So we're going to try to derive an equation with I in it. And then you can substitute it I with mr squared for the hoop. And you can replace it as 1/2 mr squared if you're dealing with a disk. Okay, so the approach is very much similar. I'm going to do a little setup here and I'm going to show you the answer. We're going to use a conservation of energy approach. We are going to use a system of the object plus Earth. The object could be the hoop or the disk, depending on which one you're looking at. The initial moment is when your object is at a height h. The final moment is when it reached the bottom. Okay. And we're going to look at the energy terms. The energy at the initial moment is purely potential energy. So that's mgh. The energy at the bottom is all kinetic, but kinetic energy has two parts. One is mv squared, 1/2 mv squared. One is 1/2 I omega squared. So in this case, we don't consider the translational kinetic friction, so that we don't have to think about energy output. There is no energy input either. So let's put that into your energy equation to solve for velocity. You can see it's just as the same as before. Omega, you can replace it with V over R. Okay, so my kinetic energy is 1/2 mv squared plus 1/2 I omega squared. Omega becomes V over R. Since I want to calculate V, I'm going to move V together outside of my parenthesis and set it into a conservation of energy equation. And that is equal to the potential energy of the object. So you have derived the equation for the velocity of the center of the mass. You can see that this equation depends on M, depends on R, depends on I. For different shapes, you can plug in different results. So if you were talking about a ring at this point, you can say, well, for a ring or a hoop, since its I is mr squared, let me plug in that into my equation. So you will say mr squared divided by mr squared. This becomes 1, right? So this becomes 2gh over 1 plus 1, and that is square root of gh. So that's for a hoop. For the disk, the I is 1/2 mr squared, which means you will plug it in here. Do 1/2 mr squared over mr squared. You get a 1/2, right? So 2GH divided by 2/3. So you get 4GH over 3. So that's for a disk. And you can see that this is 4 over 3 GH, this is GH. So that is larger than square root of GH, which means the center of the mass for the disk is larger than the center of the mass of the hoop. Well, obviously, disk move faster, right? So we're going to reach the bottom first. Okay. So any questions about this particular problem, or including the yo-yo, because you can see the approach is very similar in these two problems. We're simply using a direct conservation of energy approach to solve it. The only difference from all the energy problem we solved before is now we added another term for rotational kinetic energy. Before, we only had 1/2 mv squared. Now we added a 1/2 I omega squared. That is the only difference. So any questions so far? Any questions so far?
Could you go back to the previous slide for a second?
This one?
Yeah. Thank you. Oh, I got the picture. If you're ready to move on.
Okay, so anybody else? Thank you. Anybody else have any other questions about our energy approach? Okay, so now let's move on. Remember in previously, a problem can be solved using an energy approach, which means that you can also solve it using a dynamics approach. We could solve these type of problems using Newton's second law for rotation. It just will not be as straightforward. It's not as easy, but we can still do it. So let's do a little bit more practice on the Newton's second law for rotation. And then we could solve the disk problem, the hoop race problem, using a different perspective. All right, so let's start out with a quicker question with two disks that's been pulled by the same force. You can see that they're rotating with omega 1 angular velocity for 1 versus omega 2 angular velocity for 2. So the two disks have different shapes. Disk 1 is larger, much bigger radius than the other two, but they have the same moment of inertia. So they must be made of different material. So the one that's larger must be made of light material so that overall they still give you the same I. Now the question is, which disk will have the biggest angular acceleration? So we are going to use Newton's second law. So remind yourself what that is. Is torque is equal to I alpha, right? So we're going to use this to help us solve this question. So which one has a large alpha? Okay, I'm going to go ahead and let you vote on this. And take a minute to vote. All right, let's take 10 more seconds to wrap up with our votes. All right, any last minute vote? Okay, so I'm going to end this. We'll take a look. Much tied between this 1 and 2. So there are quite a lot of different variables inside, right? We have to figure out, well, what are the variables that are same for both, which variables are different. So we can figure out which one has a bigger alpha. So you can see that if we use Newton's second law approach, torque equals I alpha, we have the same I, which was already given. No matter how they achieve this, but they have the same rotational inertia. So if that have the same I, basically the question is which one has a bigger torque, right? So if the torque is bigger, which means that's going to generate a bigger angular acceleration, given the same rotational inertia. Okay, so which one generate a bigger torque? It looks like. Is it disc 1 or 2? Given the same force, it's the disc 1. Thank you, Jacob. And why is it disc 1 but not disc 2 if the force is the same? Okay, Berenice, were you speaking? I think I was having a little trouble hearing you.
Yeah. Can you hear me now?
Yes, I could.
Oh, I was just saying that disc 1 has a larger torque because it has larger radius and therefore it takes more force to rotate the disc rather than the smaller one, which has a smaller radius.
Very good. Thank you, Berenice and Jacob. Torque is, again, let's not forget the definition for torque. Okay, so when I wrote 3 little short lines, by definition, R cross F, R is the center of rotation to where the force is applied. So in this case is F times the radius. This one has a bigger radius, will generate a bigger torque. Consequently, will give us a bigger alpha. Okay, so the answer is A. But if the problem is changed, they don't have the same moment of inertia, then you have to really look at 1/2 mr squared to be careful to see which one has a bigger I. Okay, so if the situation is changed, you need to know how to solve it. Okay, so for the little bit time we have left, I want to be able to show you guys the same problem but using the dynamics approach. Okay, so hoop is rolling down a ramp. We have solved it previously using conservation of energy. We can also use Newton's second law. It's not as easy, but it's doable. Okay, so how do we do that? We'll see. Now, so in this case, when something needs to start rolling, we said we don't have to think about kinetic friction, because kinetic friction is when you slide, it's going to give you a friction in the opposite direction. But you do need to have static friction in order to roll. Okay, so without that static friction, it's impossible to roll. Okay, so that's we didn't talk about that explicitly, but to do a dynamics approach, we have to be very explicit about that. So we're saying there's no kinetic friction, but there is static friction. Okay, so you might wonder, well, why is this static friction? Isn't the object moving? Well, the object is moving, but it's rolling. So for it to be a kinetic friction, it has to be sliding, so that the same point that is contacting a contact point between the object and the ramp, there has to be some motion along that contact point, and the friction will be applied on the same point. But you can see what is rotating each point will contact with the ramp just at that moment, and next moment the point will be rolled up and another point will be in contact. Okay, so this is actually a static friction that is responsible for the rolling. Okay, it's kind of like the static friction that's when we are walking, there's some static friction involved as well. Certainly not kinetic friction because we are not sliding on the floor, right? We're walking. Okay, so the static friction has to be pointing up the ramp because that's the only way the object is rolling down. You can see that it's generating a torque so that the object is rotating clockwise in the direction of going down the ramp. So if we plug in torque equals I alpha, we use R times static friction is the torque. And the torque is corresponding to a clockwise rotation. That's negative Z direction. That's why I added a negative sign. I for a hoop is mr squared. If it's a disk, you can use 1/2 mr squared, okay, times alpha. And alpha is in the direction of clockwise, so it's a negative of that alpha as well. And alpha times R is equal to A. Okay, so that's, we have already seen this. Angular acceleration is related to linear acceleration by radius R. And this comes from rolling, again, rolling without slipping. V is omega R. So dV dt is equal to d omega dt R. So dV dt becomes A and the omega dt becomes alpha. So this is a condition for rolling without slipping. Now you're familiar with it, you're able just to write it down right away. Okay, and then we use also Newton's second law, because this is a Newton's second law for rotation. This is a Newton's second law for translation. In this case, it's both rotating and translating. So you have to use the regular Newton's second law as well. Now this is for the center of the mass. Okay, so this force, the acceleration is the acceleration of the center of mass, which is going down the ramp. So if you are able to, if you view the object from far away, and you can't even see that's rotating, all you see a point. So what you see is a point going down, and that's the equation you will write down, right? F equals ma. Now the force involved is the component of gravity. So this should be familiar already, is mg sine theta, that's the component of gravity, minus the static friction is equal to m times acceleration. This acceleration is acceleration of the center of the mass, because that's what it matters when it's going down the ramp, is the point, center of the mass point that's going down. These two combined, this equation and this equation combined, you can solve A is equal to 1/2 g sine theta. So when we have just one point, remember, when we only have one point, if it's a block going down, it's simply just g sine theta. Now is a hoop rolling down, it's 1/2 g sine theta. So the difference, because now we added the rotation. Okay, and then combined with kinematics, you can solve for the velocity. Very similar as before, right? Final velocity is initial velocity, which is 0 times 2a delta x. A is 1/2 g sine theta. Plug in delta x is how long the ramp is. So let me draw a little quick diagram here. Theta, h, and delta x. Sine theta is h over delta x. So you know that delta x is h over sine theta. The reason I do this is that your final result will be represented using h. That is the only variable you want to use, so that you get a final result square root of gh. Now recall, this is the same result we got before, right? Is square root of gh. You can see the dynamics approach is a little bit harder, but it's also doable and you should get the same result as you got for conservation of energy. All right, okay, so that's all we're going to have time to do today. Wednesday, just want to remind you there's no class because it's our second midterm. So make sure that you have time to prepare, including doing your practice exam, and it will be available midnight on Wednesday and available all the way until the end of the day, 11:59 p.m. So any 2-hour period you can find uninterrupted time, you can do your midterm. All right. All right, any questions before we end today's class?
Will the format of the test be like the last one?
Yes, it will be very similar, yes.
Okay,
Mhm.
cool. Thank you, Professor. Have a good day.
Will we get a chance with partial credit as well, like last time, for the FRQs?
Yes, you will. I built it I built it so that you could just submit your partial credit, your work at the exam, but not later. But the way I built it is if you have already answered correctly, the numbers correctly, then there's no need for me to look at your work. But if you answered incorrectly, then I will look over the work and correct your score. But you will submit your, upload your work during the exam. Yeah, Roseli asked, where are the solutions to the practice exam? It's under the week, I believe is week 10 folder module. It should be there. If you have trouble seeing it later, let me know, email me. What chapters does the exam 2 cover? It covers energy, work, momentum, conservation momentum, all these chapters. So 2 big topics is momentum and energy. Those will be covered. Any other questions?
Oh, so then you said we're taking the test on the same, I mean, we're submitting our work at the same time as the test. So if we're taking like the device on a computer, and I'm sorry, if we're taking the device, if we're taking the test on a computer, and we can't really like take pictures well of our work on a computer, is it okay then to like during the test try and take pictures on your phone and then get that to your computer?
Yeah, I
to turn in?
assume, yes. So you're taking tests on the computer, but I assume that you have scratch paper where you calculate it, right? So you could, of course, take a picture of your phone. Well, you have to take a picture using your phone, otherwise.
Okay.
I have a question.
Yeah.
Is it okay if I have like digital scratch paper? So like on my iPad, I just like write out all my solutions. So can I just submit that?
Oh yeah, absolutely. Yes, of course, that's okay. Yes, I will give you an extra 20 minutes on this test because given the time of uploading, sometimes it takes a little time. So the 2 hours test time, but what you will see is 2 hours and 20 minutes. The extra time is for uploading your work. All right, any other questions? If you do think of any questions later on, feel free to email me, and I will see you on Friday. Okay, bye everyone.
Professor.
Yeah.
So just to reiterate, the test will cover like momentum, energy conservation, and center of mass, correct?
Yeah, momentum conservation. The 2 type of collisions where we solve problems on that. Yes.
Okay, thank you.
Sure. Okay, bye-bye everyone.
Professor, I actually did have one more question. Sorry.
Yeah.
So I want to know if you can go back to your slides really quickly. And it was the problem we were dealing with.
Which one?
The problem dealing with
this one?
With the hoop and then the disc. I mean the ball and the block. The bridge question.
I see. This one?
Yeah. So I'm a little bit confused on why the ball would have more energy if for instance for the problem that we did with the block and the ball, we had said that the energy was conserved because they were at the same point and then they had the same fixed mass. So then I'm a little bit confused on why here it has more kinetic energy, even though
That one they are rolling down from the ramp. They all start out with the same height. So let's say they are all given 100 joules, and then they use it in their own way. But the block is all used to kinetic energy translational. For the ball need to use the same 100 joules between translational and rotation. But this is different. This is not giving the same energy to begin with. You can see for some reason you have given the ball more energy to begin with than the block. So in this case, this is 100 joules, this is more like 150 joules. But you don't care where it comes from. Someone gave them the energy and they use that energy to go up because it's a reversed order. Does that make sense?
Okay. If like we're given a problem to solve, it should tell us like the energy being added to the object.
Yeah, so if it's a problem where they were from the bottom of the ramp having the same V, so this one only have the same V. This one has the same V, but also rotating. You know the ball has more energy to begin with.
Right, because it has rotational and translational.
Yes, that's correct.
Okay, so then when we have rotational and translational energy together, it's not like distributed. Like for instance, like if we like for instance, like if it's 100 joules, like it's 100 joules distributed between translational and rotational. Does that make sense? Like
It's rolling down from the same height. Yes, that's correct.
okay. Okay, thank you.
Okay. Bye-bye.